We are Team 8. I'm Rasean.
I am Ritu.
I'm Jinan.
Ike Kabir.
And this is our presentation on preventing plagiocephaly.
The problem we're addressing is plagiocephaly in infants, a condition known colloquially as flat head syndrome, which can be congenital, meaning it's present at birth, or positional or deformational, meaning it develops during infancy. The prevalence of the condition has increased 600% since the 90s and affects around 47% of infants today. This colossal increase can be attributed to two lifestyle changes in the past 20 years. The first being the Back to Sleep program to reduce the incidence of SIDS, sudden infant death syndrome. The Back to Sleep program was an incentive proposed by the American Academy of Pediatrics that urged parents to put their babies to sleep only on their backs to reduce the risk of suffocation. And it worked. The incidence of SIDS was reduced by almost 40%. However, since babies were then spending more time on their backs and sustaining more pressure on one side of the head, plagiocephaly rates began to rise. The second lifestyle change that has influenced the increase of plagiocephaly is the increased amount of time infants are spending in carrying devices. Families are now very active, they're always on the go, and are now keeping their babies in carriers, car seats, and swings for an extended period of time, frequently up to 15 to 18 hours per day. The graphic on the top right corner demonstrates the difference between a healthy head and a plagiocephaly-affected head. The plagiocephaly-affected head shows flattening on the right side of the baby's skull, while the left side protrudes outward. If left untreated, this can lead to functional challenges as the child ages, including cognitive and motor delays, visual impairments, and noticeable facial asymmetry. These medical conditions can result in a child developing other, more serious medical issues down the line. For this reason, it's vital to prevent the condition from occurring in the first place, which can be achieved through practicing good head positioning during early infancy. Current devices on the market, such as cranial helmets, attempt to correct the condition as opposed to preventing it. This can be very expensive. Other devices attempt to prevent the condition by only decreasing the amount of pressure sustained by the head, but they do not address the amount of time spent in the same position. An ideal solution functions to address both. It's also financially viable to prevent plagiocephaly. For example, since it can lead to jaw misalignment, an inexpensive device for a baby can prevent having to get $5,000 braces as an adult.
Our problem statement is a method to facilitate proper head positioning in infants aged 0 to 4 months to prevent the onset of plagiocephaly and ensure healthy head growth. It is ideal to reposition infants from 0 to 4 months. The first reason being the skull is most malleable at that age. And the second reason is most infants start moving on their own after 4 months, making repositioning difficult. To conquer plagiocephaly, we propose a biocompatible and a crib-compatible device designed to redistribute infantile cranial pressure and reduce the time the infant spends in the same position.
There were 4 main changes made from the LoFi to the Hi-Fi device. Firstly, we changed the changing pad to a mattress so that the child will be more comfortable and the inflatable compartments will be more secure. Secondly, we changed the number of compartments from 3 to 5. This increase was to allow more intricate control over how the bed inflated while also giving more support on the ends via 2 designated outer compartments. Thirdly, we replaced the handheld pressure bulbs with a semi-automatic pressure pump. Automating the process of inflating the mattress allows for filling the compartments automatically as well as making the device easier to use. Also, at this point in our design, the pump required pushing an on-off button, making it more efficient than pressure bulbs but less efficient than a fully automatic on-off system. This was later changed for the latter, which will be explained later. Fourthly, the angle of inclination was increased from 15 degrees to a maximum of 45 degrees. According to the graphic on the right, the higher level of inclination allows for more contact area with the mattress, which means the device has a higher amount of efficiency. There were also 2 main additions to our device. We added an automated inflation and deflation system that rendered the semi-automatic pump fully automatic using relay switches. Lastly, a chassis was designed using SolidWorks to house all the components and minimize the electrical hazard during use.
In testing our LoFi prototype, 4 1.5 by 1.5 inch force-sensitive resistors set up in an array were used with Arduino. 10 kilo ohms resistors were used for changing sensitivity, and the provided datasheet from the manufacturer shows us what the data achieved represents. Using the dimensions of our sensors and the force applied, pressure could be calculated. Force detection anywhere within the area of the sensor did not change. We were testing whether or not pressure shifted from one point of the head to another. Pressure was shifted. To avoid the possibility of our data being achieved from the infant sliding on the sensors were wrapped around the infant's head. The same results of pressure shifting were achieved. Some sample data on the Arduino serial monitor can be seen on the right. Pressure readings are in pascals. We bring you our final prototype for the semester. All components arrowed are of our final design with the exception of the dummy infant. Pressure distribution is done by the inflation of a pump and the deflation of a vacuum. Air will be distributed in inflatable heat-sealed PVC pouches that are aligned in an array-like fashion with the shorter end of the compartments making the final end length. Each compartment measures 4.25 by 5 inches. The total final dimensions of the compartment grid is 5 by 21.25 inches. They will be placed 2.5 inches from the top of the mattress, near the head resting area and underneath the first layer of memory foam. Air inflow and outflow will be regulated by our servo valve platform. 5 high-torque servos are used in tandem with 3D printed cylindrical rods serving as actuators, rotating the valves for inflow, air sealing, and outflow. The platform is a wooden base that aligned the rotating aspects of the servos with the valves. Wooden inserts were added to raise the mechanical components for proper alignment. The platform tremendously minimized the need of materials and maximized the cleanliness for actuating 5 independent valves. Otherwise, grit, spit, and a whole lot of duct tape would have been used. An Arduino board served as the heart of the design in controlling the servos, the pump, and the vacuum automatically. Timing intervals of varying pressure distribution was programmed. Power is supplied by a wall outlet and into a custom-built power extension box. This was done with 2 electrical outlet boxes and 2 receptacles. One receptacle shown in the rightmost photo had its 2 sockets electrically isolated, with each connected to a relay module, which the Arduino would toggle on the flow of power to these sockets. This would turn on or turn off the vacuum and pump automatically. An AC to 5V 700 mA DC USB converter to micro USB, pictured on the left, powers the Arduino. An AC to 5V 4A DC converter with a power jack to 2-pin terminal adapter, pictured on the right, was needed to power the servos. These power converters were connected to the other receptacle of the power extension box. Ultimately, a chassis was intended to house all electrical and mechanical components of the design, with the exception of the PVC compartments and partial length of the tubing. The chassis is not present at the recording of this video. Our design would classify as a Class 2 device because of special controls with electronic components. Our device is substantially equivalent to a predicate device, an alternating pressure air flotation mattress. This predicate device is intended to alleviate pressure soreness in bedridden users. Our design prevents infant skulls deforming during pressure soreness. Our design should provide safety as the infant should only have physical contact with the mattress. The mattress has 3 layers of hypoallergenic memory foam. The dimensions of the mattress should comply with national standards for crib mattresses. These last 2 specifications are met as our mattress was acquired from Amazon measuring 25 by 25 by 4 inches. Our device should alternate pressure by inflation and deflation every 2 hours. Babies are on their backs for an average of 18 hours. 2 hours was chosen as an optimal time to ensure pressure distribution and avoid disturbance to an infant. Alternate inclination on one side of the mattress at 45 degrees would shift the contact of pressure on the infant. Smaller angles have proven to do the same, but 45 was chosen that would optimally shift the contact of the pressure away from the sutures of an infant's skull, which are more prone to deformation than the rest of the skull. Each PVC compartment should be the following dimensions and placed 2.5 inches from the top of the mattress to be regional specific to the infant's head. Placement of the infant at different locations on the mattress with all appendages within the perimeter of the mattress did not impair functionality, as head rotation was still observed. The 2 specifications denoted by asterisks are to be kept in mind. As Ritu said earlier, we are testing for these 2 at this point. Due to our unique circumstances, we were not able to address safety, so the PRD items we chose were based on the mechanical parts of the design as opposed to anything quality assurance based.
We chose to test these 2 PRD items solely based on the mechanical functionality of our device. The first PRD item tested whether an inclination of 45 degrees would rotate the infant's head horizontally off axes. If this PRD item was satisfied, we would then test our second PRD item, which is whether the pressure at that angle was redistributed over periodic time intervals. The most feasible time intervals would be a rotation of the infant's head every 1 to 2 hours, depending on the infant's sleep schedule. To test for the 45-degree angle of inclination, a doll will be placed on the pressure compartments. Various air pressures will fill each compartment to create a 45-degree angle of inclination. The test would fail if the infant's head does not rotate from one compartment to another at a 45-degree inclination, and it will pass if the doll's head rotates from one compartment to another. If the test fails, we will test for a different angle of inclination to rotate the infant's head. We will indirectly be testing the redistribution of pressure by testing for the redistribution of force. The force will be tested by placing 3 force sensors on the middle 3 pressure compartments. Then the weighted doll will be placed on the centermost compartment. The infant will then be rotated at an inclination using air pressure according to the previous PRD item. Each force sensor will output a force in newtons. If the force redistribution is greater than or equal to 30% from one compartment to another, then the test will pass. If the force redistribution is less than 30%, then the test will fail. In that case, measures will be taken to reevaluate the air pressure in the compartments. Our design was motivated based on engineering and physiology concepts. The figure on the right shows a skull with sutures. Physiologically, the skull growth occurs at suture sites. Hence, it is important to distribute the pressure away from the suture site. This can be done by holding the parietal bone to give rhomboid suture room to grow. Research shows that sutures can be upheld by rotating the head at an inclination of 45 degrees to distribute the pressure. For this, we'll be using engineering concepts. As previously mentioned, we'll be testing for the force, which is correlated to pressure, by the equation pressure equals force over area. The force sensors will output a force reading that will help us identify if 45 degrees is the best angle and assure us of the pressure value that can minimize the deformation of the head.
Because of unforeseen circumstances, physical tests could not be performed, so statistical analysis was performed and this estimated data was supplied. As can be seen from the table, each 5-degree increment has 3 corresponding numbers. Read from left to right, these correspond to the sensors that were placed underneath the doll's head, on the left, middle, and right side of the head, as the values in the table are the amount of force in newtons applied to each sensor. Of the 3 sample tests run, it is consistent across the board that the force was successfully redistributed between 30 and 35 degrees as the values increased substantially on the rightmost sensor pad between these 2 increments. Anything above 45 degrees yielded unusable results, hence why our angle of inclination was set to a 45-degree maximum. Here is the data again, but this time more visually appealing. The x-axis represents the angle of elevation tested, and the y-axis shows the amount of force applied. Here, as the angle of inclination increases up to 35 degrees, pressure is decreased in the middle and left compartment while it increases in the rightmost compartment. The final value is 45 degrees, which is again the point at which the results become unusable.
Given the unique circumstances of having to develop our device remotely, we have expanded on the physical prototype to the best of our ability. We are grateful to say we have completed about 90% of the basic design and we're satisfied with where we concluded. The motivation to finish was based on how far we've come from our initial prototype iteration in such a short amount of time. As our project sponsor, TJ Elgato, so wisely stated, the end product is not as important as the lessons learned working together, such as the process and teamwork it takes to come up with a solution. We have shared our design process with TJ from start to finish and have received feedback on next steps, which would primarily include testing for safety and efficacy. We see a potential in our design in the competitive landscape, so we plan to move forward with the development of the device under his guidance. Before the unprecedented circumstances regarding the pandemic arose, our original plan included testing the device with sensors in a weighted doll with a rotating head. Pressure, angle, and force tests that we were hoping to conduct were ultimately replaced with mock data provided by the TA. Additionally, we plan to incorporate a pump button actuator to further automate the design, as well as a method to rotate the infant on a semi-customizable time-based interval. As for our future plan, we plan on testing for efficacy and safety, which is the most important PRD item that we were unfortunately unable to test given the circumstances. We will also implement a more silent operation, given that our current one is pretty noisy and would most certainly wake any child within a 5-mile radius. A swaddle will be incorporated to further ensure safety and comfort. And lastly, aesthetic improvements will be explored, such as an improved chassis to house the components, redesigning the actuators, and reducing the size of the device in general. We would like to extend our gratitude to our project facilitators and sponsor, as well as all the resources provided to us by the BioE department and the UIC Makerspace. We'd also like to thank our classmates for their valuable feedback over the course of these 2 semesters. Thank you all for the opportunity, and we hope you remain safe and healthy during this time.